Okay, we're recording. For the past maybe 6, 7 minutes, I've been trying to log in from my tablet. So if I get kicked out again, I don't know what will happen. It will take a while to get back in because there's this single sign-in security protocol now in Zoom, which sometimes takes me to unknown pages. But anyway, I got in. That's the good news. Is there any question about the material we covered yesterday? Let me actually probably review it first. And take it from there. Okay, so I did an example on chaotic dynamics, a non-trivial example in which we had to use essentially the full extension, the full power of symbol spaces because it involved several symbols, not just two, and not all transitions from old states to other states were possible. So we needed to use a transition matrix in the encoding. I'm not going to go back to that example unless there's somebody who has questions about that. Because I discussed that in quite some detail. Instead, I wanted to just briefly recall the new subject that I got started on, Hamiltonian systems. So hopefully pretty soon you'll get a sense that if you haven't encountered Hamiltonian systems yet, it's a very important class of dynamical systems. Important for two reasons, because it arises in many different areas that are seemingly on the surface unrelated. And second, the special structure of the equation enables us to reach conclusions without doing any work globally. As some of them are local, some of them are global. So it's very important to be aware of the properties of Hamiltonian systems, because if you see one, you immediately know a lot about the system without having to do any work. And that is a big help because the system, mind you, is fully nonlinear and potentially has very high degrees of freedom. This might be a molecular dynamics simulation with hundreds of thousands or millions of degrees of freedom. And it's very helpful, which also turns out to be in the Hamiltonian framework, it's very helpful to have some a priori information about what you can expect. So a canonical Hamiltonian system, this is a larger subject, but I'm restricted to canonical Hamiltonian systems, is one that is even dimensional. It's always composed of two different kinds of variables. Q is often referred to as generalized position. P is often referred to as generalized momenta, the elements of that, even though this might not be a mechanical system. And you put the two together to form the phase space. And it's enough to know a single scalar function. So these might be hundreds of thousands of dimensionals, or if not millions, right? And yet the full equation, when you want to reproduce the equation, the full equation can be reproduced from a single scalar valued function of these variables, which is the Hamiltonian. Generally also depends on time. So this is a Hamiltonian associated with this system, and it has this important skew property relative to a gradient system, whereby you would simply take the gradient of the Hamiltonian here. You, as we have actually seen, you can take the gradient, you start out by taking the gradient, but then you do a rotation on that gradient, which in the canonical case can be described by this canonical symplectic matrix, which is simply a skew-symmetric matrix that you build out of the identity m by n identity here and minus m by n identity there. Okay. One way to generalize the Hamiltonian system notion is that you allow for a more general matrix here, but that matrix cannot be arbitrary. At the very least, it still has to be skew-symmetric to have the types of conclusions that we will have to reach. But already a lot of systems fall in this particular framework. Okay, so if there are no questions, probably there are no questions yet about this, because this is really just the beginning. I would give you a few examples just in case, basically just to fix notation and either remind you that you've already seen these types of systems, but perhaps you didn't recognize that they were Hamiltonian or was not pointed out to you, or even if you have seen them, there are some other areas which you potentially have not seen. The first is, which I believe was the original motivation, is mechanical systems. Although I will say that if you take a standard course in mechanics, you will probably not hear the term Hamiltonian at all these days. probably because you know, the mechanics curriculum has to be optimized, and there are so many other things that need to be taught at the introductory or even at the advanced level. So this somehow is viewed more of a very advanced subject, or sometimes an esoteric subject. So mechanical systems that are holonomic, and a holonomic mechanical system is one which only has geometric constraints. So when you think about introducing coordinates, there will be constraints in the geomechanical systems, and your system coordinates have to conform to those constraints. And there are different types of constraints, and geometric constraints only involve positions. So these only involve positions. So you basically start with, you know, our eyes are labeling the positions perhaps of point masses in your system. That's a vector, okay? And normally when you describe a constraint, then you would also throw in the velocities. That's the most general form of constraining mechanical systems. But in these ones, the constraints only relate to positions and potentially in time. So you may have, you know, J of these. That's not something I want to go into. It's the subject of a K of these mechanics class, right? But this is what you start out with before you start adding introducing coordinates. This can be as simple as a slope, right? So if you want to introduce a coordinate for a ball which is moving on a slope, then it's much more economical to take that slope into account, that you're confined to that slope anyway, and introduce a coordinate only along that slope, rather than write down the motion of that point mass as a general one in a two-dimensional plane and try to figure out how that is constrained by the plane, right, or the slope. So you introduce coordinates to begin with that are conforming to the constraint, which is that the point mass has to move on that slope, right? Now the slope itself might be moving, okay, at which point, say, at uniform speed, then this is a time-dependent constraint, because at any point in time you will know one constraint on the point mass, which is its position. It has to be on that slope, but you're not constraining the velocities, because the velocity relative to that slope can then be arbitrary, and hence the total velocities, other than the fact that you're constrained to the slope, is arbitrary, right? So they have to be holonomic. And the other assumption, the only assumption that we need, is that all forces are potential, all external forces. Well, just forces. No. On math, how do I write this? You can have internal forces as well, but let's just. So whatever you add to the equations of motion to, say, individual masses, which would still be in the form, say, in the simplest case, mi times ri, you know, double dot, and this is without the constraints. Whatever the forces would be acting on the ith mass, there's no summation on the left here, can be derived from as a negative gradient of a potential. So this is the potential function. And we learn in mechanics to derive equations of motion for these. And the most pedestrian way would be Newtonian mechanics, in which you do not, at this point, include the constraints in the derivation of your equations of motion, but basically throw them in afterwards. The alternative way would be using the Lagrangian approach, in which you introduce generalized coordinates that are already conforming to the constraints. So with generalized coordinates, say generalized positions, qi, or let's call this qk, and k here goes from 1 to capital N, and N is the mechanical degree of freedom of the system. The Newtonian equations of motion, which I just referred to as the classical equations of motion, are equivalent to what we call the Lagrangian equations of motion. And the Lagrangian equations of motion would be in this form, the partial of a Lagrangian function with respect to these coordinates, the generalized coordinates, which I now write as a vector, minus the d by dt, the time derivative of the derivative of that, again, single function L, the Lagrangian. I'll get to that in a second, with respect to q dot equals 0. It's a vectorial equation, right? And what it turns out to be, this is a second order equation. The reason why this is a second order equation is that, well, I have to say what L is. L is the Lagrangian associated with the mechanical system. And the way you calculate the Lagrangian in general is that you take the kinetic energy. Okay, I need to point out what L depends on for that. So L is a function that depends on Q, the positions, the velocities, and time in general. And what it is, it's the difference of the kinetic energy, T, Q, Q dot, minus the potential energy which is associated with those forces that we discussed. But now it's expressed in terms of the generalized coordinates, but not the velocities. So velocity independent potentials are assumed. So that's the Lagrangian. This is the kinetic energy. And this one here is the potential energy. Okay, so that's something we teach in mechanics, and we derive this relationship. So we do show that with these quantities and using the difference, interestingly, of the kinetic and the potential energy, not the sum, but the difference, this particular function can be used to recast, the Lagrangian can be used to recast the original Newtonian equations of motion in this form. You have n, and this is since Q is an n-dimensional vector, you have the n equations, n being the degree of freedom, and individually these equations, just look at how they are derived. You differentiate the kinetic energy, which is generally a quadratic function of velocities. So you get this practically a linear function of the velocities. It will also have a dependence on Q, but it's a linear function of the velocities. And you further differentiate that. Now see that will then introduce second order derivatives of Q, but also first order derivatives because there's dependence on Q, and you also differentiate with respect to T. So make a long story short, this is a second order set of ODEs. So these are not first order ODEs, the ones that we typically look at this class, but they are individually second order, generally nonlinear ODEs. And from a mathematical point, actually, the mathematicians very often prefer this set of equations over Newton's equation because this reflects a variation. It can be related to a extremal or stationary value type description of the motion. We tend to think of things taking place in nature for a reason because they either minimize something or maximize something. In some cases, they are stationary values of something. So basically a saddle type stationary points of a functional. And this formulation is related to that. In fact, those of you who might be familiar with calculus of variations, you would recognize this equation in a more general context. It's the Euler-Lagrange equation that you obtain when you have a variational problem for this function L. So in the mechanical context, that's the variational formulation is the principle of least action. I don't think that this is how these were derived, the way these were derived first, the equations of motion, is that people were playing with Newton's equations of motion, and they were trying to find ways to derive the equations, equivalent equations of motion for coordinates that already incorporate the constraints. So what I didn't say here is that the general positions, these already account for the constraints. Like when you move on a slope and you introduce a coordinate which is along the slope, right? As opposed to wasting your time on describing the motion in full 2 dimensions and then trying to add additional constraint forces, right? So we select the generalized coordinate which is along the slope. So these already account for the constraints. And as such, they can be essentially anything. Most often their positions or angles. And, and people were then introducing these coordinates, which are ultimately coordinates then satisfy these pre-existing constraints. And they were trying to see that instead of going through the Newtonian machinery, right, which is quite clear for point masses moving in unrestricted in an n-dimensional space, how could they directly get to the equations of motion using these generalized coordinates, which are no longer necessarily positions? I mean, you may have a scalar coordinate even though your actual motion takes place in 2 dimensions, or your coordinate might be an angle, right, for which that this formulation doesn't directly apply. And as people were playing with that, they were arriving at this equation of motion, and then they said, wait a second, I've seen this, I'm exaggerating, but this sort of I'm paraphrasing how this discovery went, but then by analogy, they discovered the principle of least action, sort of backwards engineering. At least that's the only way I know of how it's ever been derived. And it just said that, well, if I now describe, set up the following variational problem. This is the time axis. So this is going to be the extended space of positions and time. So this is my Q1 generalized coordinate, and it goes up to Qn. So what we have here is time in this direction and everything else. So the position space, the state space, is here. Then I might ask, suppose I know that at time t0, so I project it down here, I was here. Somebody tells me in this space time. Somebody also tells me that at time t1, I was here. Somehow I know these 2 endpoints. Okay, so this is my motion q described by the generalized coordinates at time t1, and what I'm pointing is a pairing, right? Q t1 t1 right there, whereas this one is q t0 t0 at time 0. So in this extended phase space, and I could have gotten from point A to point B in many different ways. I could have gotten this way, I could have gotten that way. So I can ask the question, why did things happen the way they have happened? Just give me the 2 endpoint. Why did I exactly move this way, the way I have moved? And the answer to that, apparently, look at the equation of motion, that the actual motion that took place between those 2 points, once I fix those 2 endpoints and I look for admissible motions, potential motions that are fully consistent with the constraints, then by backwards engineering, this is the Euler-Lagrange equation, variational equation of L, which if I set up this problem, integral from t0 to t1, L, yet unknown path, Q of t, with unknown velocities, Q dot of t and t, dt, and I try to extremize this quantity. This is just the principle, this is the integral of L, and there's no a priori reason why I would be interested in it. That's why I'm saying is this is reverse engineering, because L is not a natural physical quantity like sum of energies or anything. No, it's the difference of 2 energies, right? And it's not a natural quantity to think about. So I'm sort of reverse engineering and say, okay, if I take the variational derivative of this one, in other words, I evaluate this function, this integral, along all possible paths, okay? And I have a parameterized family of those paths, and I look for an extremum point around which this integral, not necessarily extremum, but would have a stationary value. In other words, this derivative is 0. Then the solution of this problem, these two fixed endpoints, is precisely this equation by calculus of variations. So by this analogy, people said, okay, so the equation of motion is equivalent to something, and I think it was actually Hamilton, if I'm not mistaken, who called this the principle of least action, which is simply a postulate that, you know what, this is equivalent to this problem, to taking just sort of ad hoc the difference of two energies and setting up a variational problem and requiring this integral to have a stationary value along the particular motion that will be realized. So that's called the principle of least action. And by calculus of variations, this is equivalent to the equations of motion star. So it's basically this principle or requiring double star. Well, and then double star. So this is double star. So this is what you see here is Newtonian mechanics. This is what you see is Lagrangian mechanics, essentially. That's how we teach it. Oh, you can do more than this, right? I mean, there are variants of Lagrangian mechanics that allow for the inclusion of non-holonomic constraints. Then you will have your Lagrange multipliers and everything. It's just, this is the simplest setting that we teach as Lagrangian mechanics. So Newtonian mechanics, Lagrangian mechanics, and if you will, variational mechanics, which actually can be further twisted into other type of mechanics that people then call Hamiltonian mechanics. So let's now look for an further alternative formulation. And to be honest, again, I think that I tried, finding an actual well-grounded motivation for what I'm going to do. But I think, again, this was just noticed by reverse engineering as people were really trying to find the optimal, simplest expression for the equations of motion, right? Why would they keep working on this equation further? One drawback, if you will, from an analysis point of view of this system is that it's a set of second-order equations, okay? And also the form of it, even though you just need one scalar function here as well, the form of it is a bit complicated. That's the second drawback. And the third drawback, I would still say that when you work with this and you try to have physical intuition for things, it's hard to have physical intuition for the difference of the potential and the kinetic energy, right? It's not something that naturally comes out from extreme principles, right? So that's why people are still massaging this in ways that would potentially simplify this. So here's the next step. This assumes something. It doesn't always work, but it works for most mechanical systems we know. Assume that this Lagrangian L Q dot T, all right, is a convex function of Q dot. Why is that a reasonable assumption? The Q dot dependence of the Lagrangian, let's just see where that comes from. Q dot dependence is entirely coming from the kinetic energy. And the kinetic energy, whatever the details are, right, it's reasonable to assume that it's a convex function. So the kinetic energy doesn't react to the sign of Q dot, just to be simplistic, right? It reacts to the magnitude of Q dot. And also when the Q dot, the velocities are small, the kinetic energy will be small. When the velocities grow, kinetic energy will be larger, right? So this is not at all an unreasonable assumption to make, and it's makes the approach very general. If that is the case, then if I draw now a graph whereby I'm simply showing, this is a generalized graph, right? Q is a vector, so what I'm doing here is hand waving. It's not, Q is Rm. So this is a hand waving graph representing a whole plane, if you wish. And I'm going to show this function, the scalar function, which is q, and you know, I just put a dot here because I'm showing it now as a function of the q dot variable. All right. So q and t right now are fixed. So I'm showing it entirely as a function of q dot. And what I have just assumed is that it's a convex function, not complex. So, you know, something like this. It's a scalar function. So then, so here goes the story. Okay, so in this domain where it's a convex function, I can just query the value of the Lagrangian. So this is graph L. So I'm just evaluating its value there. That's what I'm going to do. And L is differentiable. What I can do, I can look at its tangent here. Again, this is hand waving for the purposes of a picture. In reality, this will be a tangent plane. All right, but right now, since I can only draw a one-dimensional q dot, it's just a tangent line. So what this is, it's tangent to that point. So how do I show that? So, you know, the slope here of that angle that I'm showing here is dl d q dot taken at that point. This is just some q dot that I started out with. Nothing fancy so far. Here comes the idea that I really cannot well motivate for you, and I have not seen a good motivation for this. It's basically a reparametrization of the whole Lagrangian problem by a different coordinate, a choice of a different coordinate, and I would be lying if I said that that's an intuitive choice, not to me at least. The choice is the following. I can take this slope that I have here, and I simply extend it from the origin, the exact same slope from here. So this should be parallel to that, right? So this line is parallel to that line. I just take it and subtract it. And I will introduce a new coordinate to parameterize L, which will be the difference of what I'm seeing here. So precisely this distance here. Maybe use another color. So again, the procedure would be at q dot, you figure out what the slope is. Generally speaking, this is a tangent plane. And you take that tangent plane and shift it to the origin. Okay. So at that point, when you're done with that, the equation for what we're showing here is you took the derivative TL dq dot. Okay. And if this was just a one-dimensional setting, then I would simply multiply this by q dot, and that would be the equation of that line. But since this is a plane, I have to take the dot of that. Okay. And what we're seeing here is the graph of that function. That's what I'm doing. Okay. But I'm not done. But instead of, I actually want to replace the q dot coordinate, which I have here, and this is very intuitive, with this difference as a new coordinate. And then that difference is then called h, and you can then imagine where this is leading, why I call it h. But it's basically a new coordinate, and what it depends on q. It depends on the derivative of L with respect to q dot. It depends on t, and I simply write out what I see there. Okay, that simply the definition of that is this length, the distance between the two planes. It's a scalar distance, even if we're talking about planes. The shifted tangent plane and the graph of the function. And the way I got it, I had this expression here. Okay. And what I did, I simply subtracted L at that point. And L, I should point out the dependencies. I forgot to write that. So L depends on q dot t. I dotted that with q dot, and I subtracted L q dot t. Okay. At this point, I don't know what it is, but I can, on any convex function, because all I used here is the convexity of this, I can perform this operation. And not yet, but when I'm done with this change of coordinates in my problem, this will be called the Legendre transform of L. It's a transformation that acts. So this produces this new coordinate. I think at this point, just call it the Legendre transform of L. At this point, you feed in a function L as a function of Q dot. The other two variables are fixed. And what the procedure gives you a new function. It's again a scalar function. Okay, but this is the operation that you had to perform on the original function. And in order for this to work, you had to have a convex function. Okay, and again, this is my best. A lot of the books, in fact, that you see in mechanics don't even have this picture or any explanation as to why this is. You just say, here's the Lagrangian, let's define the Legendre transform of the Lagrangian, and just take it or leave it. This is it. I think at least this is the picture that I have in mind about the geometry of what we're doing here. Okay, so then with this, the next step is give a name to this slope, because it will come up all the time. So actually introduce the definition of P, and again, this is little p, so you might be thinking, okay, so he's heading towards something like that, and you're right. I already have this element here, and I already have that element which I have just introduced, and I had a Q to begin with. So actually I'm gearing up with my notation already to show you that this is the framework where I'm heading with this, but I had to go through this horrendous construction to get there, right? So anyway, so define P as simply the derivative of L with respect to Q dot. And that, remember, that was the slope that I was working here with, all right? And that's called, in this context, as you may have guessed, is the generalized momentum vector, or generalized momenta, the collection of generalized little momentum elements. And here comes an important point, that the convexity of L, which I have assumed at the beginning, enables me to invert this relationship. Because to any Q dot that I had here, I came up with this function, which H, that I came with. But even before I get there, the point I want to make is that for any Q dot, the slope that I'm getting out of this procedure is unique. And again, just accept that as a hand-waving argument. But in a convex domain, if you then change Q dot, you will get a different slope, right? And you change Q dot, again, a different slope. Now, if the function was not convex, but sort of repeated itself, then I could get the same slope here, and I could get the same slope there. But if the function is convex, the slope is unique. So you give me the slope, then I will give you the point at which that was the slope. So that's the idea here, that just from the slope, which I have P here, I can tell you where the point is. Maybe this is not an easy relationship, right? Maybe it's complicated, but in principle, it's a well-defined relationship. So Q dot, which is I then view as the inverse of this relationship. So I'm inverting this. Remember this, I had a Q here, which is fixed in the construct. I had a Q dot and I have a T. Q and T were fixed all the way, but I'm about to invert this relationship. And I claim that even though I might not be able to write this down explicitly, this inverse relationship exists. And that's the convexity. So that gives me a general function f, which, remember, Q and T were fixed, but I have simply replaced Q dot in the consideration with P. So whenever I see Q dot from now on in my analysis, I can use this relationship. Somebody has been trying to reach me from Rotterdam, from Holland, 3 days now. Whenever I answer the phone, they talk to me in French, and I tell them I don't speak French. Then they apologize. Then they call again. Maybe they hope I learn French in the meantime. That's all right. Okay, where was I? So this convexity that enables me to invert this relationship, and what good does it do to me? I'm almost done. I have this function here, h. Then I can, this is now p, right? And I can just simply rewrite this function as a function of q, p, t, right? And in the definition of the function, again, this is now p. So I will write p, except I really have to write it. And whenever I see q dot, I'm working on eliminating q dot as a variable. And I have, at least in principle, this relationship. So this then gives me p dot f, p, q, t. And what was the rest of that Legendre transformation? I had to simply subtract the Lagrangian, which I'm doing here. But whenever I see q dot, the whole idea of this game was to replace velocities with momenta. So then I will write an f there. It's a function of q, p, t, and t. This doesn't look very enlightening yet because the f function is general at this point unknown, yet I'm in a good position now to call this the Hamiltonian associated with the problem, or just simply with the Lagrangian L. And if somebody then asked, what is the Hamiltonian of a mechanical problem? Then there are two types of answers. You can say it's the difference of the kinetic and the potential energy, or you can just say it's the Legendre transform of the Lagrangian. It depends on your partner with whom you speak, whether this is a good answer, whether they learn something from it or not. But definitely both of them are correct, right? The first one is the more physical answer. This is the more mathematical answer. It's simply the Hamiltonian associated with the problem is the Legendre transform of the Lagrangian. Okay, not very helpful at this point because I don't know exactly what f is. So let's work on this a little bit. Again, as people were playing with this, there comes now a step which it looks highly trivial, but I don't think it is. Whoever came up with this, and presumably maybe it was Hamilton, it's very insightful. I don't know much about f, but I'd like to get an equation of motion for q and p, even though I don't know what f is, right? Can I get away with that? So you can take the differential of h, which the total differential, which is the following, given that it depends on q, p, and t. So you take the partial of h with respect to q, and then you do dq. Again, these are all vectorial quantities, so I would have to have a dot here, but I'm not going to write always that always out. What I mean here is that, you know, this is a row vector, and this is a column vector. So I'm taking the dot product there. It's implied. Just I view these as two generalized, you know, matrices of the appropriate dimensions. I can write them next to each other. Then I do the partial with respect to p, dp, and then I do the partial with respect to time, dt. And certainly I haven't assumed anything there. It's just the differentiability of h on the one hand. On the other hand, I can take the specific form of h and try to figure out what this is. Now, when I take the differential of this, then I will have first f dp when I acted in just the product rule of differentiation, which is also true for differentials. And the next one is p df, right? And again, what I mean is these are vectors in the appropriate order. These are dot products that I'm omitting there. I could go into evaluating what this is and take the differential of f, but it turns out it wouldn't take me too far because I actually don't have a functional form for f at this point. So I just stop it here and leave it unevaluated. And then I do by the book the differential of L, which is the partial of L with respect to Q, dq. Then I go for the second argument, the partial of L with respect to Q dot. And then I have this f there, which is unspecified. I know it exists by convexity of the Lagrangian, but I can't really specify it further, df. And then finally, I have the partial with respect to time. Okay, and then I make a couple of observations. The first observation, which is probably the simplest, is this quantity is now familiar. I actually use that as a new variable. So that quantity is simply P. So this is just P by definition. Okay. Well, the minute I realize that I have then reason for some happiness, because this is then here PDF. This is also PDF with the opposite sign. So these two cancel out. That's good. Now, what else do I have here? This looks suspicious. Maybe I can do something, because that's my L. I want to get rid of L in this discussion, and I don't want it to have a prominent role. I want to have a discussion in terms of age. So what's dl dq? Well, it's not so obvious from here. That's why I say that this is surprisingly not this require. And again, my highest respect for people who have figured this out, that this actually leads somewhere. You need to go back and reassess what this is, the derivative of L with respect to Q. And if you go here, you find it in the Lagrangian equation of motion right here. That's dl dq. But it seems like if I express this as a function of the rest, then I'll get something even more complicated, right? But not with the current set of definitions that I have, because this is now P. So what I see here altogether is just P dot simply from the equations of motion. So I can go ahead and replace this with P dot. And that comes from the equation of motion. Okay. One last thing, this F really bothers me because I don't know what it is, but at this point, I remind myself that F is just the function that ultimately returns Q dot. So why don't I put it there? This is by again, this is how F was defined. Okay. And then you're in a position to compare the various remaining terms in these two different expressions for the differential of age. So if this was your first version for the differential of age, and that's your second version, then by comparison, you get the following equations. So first, well, the second one still has lots of terms, but let's just see. This is Q dot dp, and the differential is uniquely determined, right? So for all I know, this term must be the same as that term. But if these two are the same and dp is the same, then I get that Q dot is equals the partial of h with respect to p. Good. So that takes care of that term. So these two terms have been taken care of. There's the other part of the differential, the dq terms. Again, these two must be equal. That means that the coefficient multiplying dq must also be the same in both cases. So that gives you p dot, and I have a negative sign there. So that's dh dq. And finally, I have one more term left. This must be equal to that. So that tells me that the partial of h with respect to t is the negative partial of the Lagrangian with respect to t, which is good to know. But what's really important here is that h I've already viewed it as a function of pqt. So I got a new set of equations of motion, now fully in terms of h. And lo and behold, this is exactly in the Hamiltonian form, right? So this is called the Hamiltonian equations of motion. And what you have here is the Hamiltonian framework, which we didn't have before, and that will turn out to be an advantage because of the symmetry properties of Hamiltonian systems. What you have is now a 2n set of, however, first order ODEs, and even a whole lot more compact notation. Okay, so if you don't have to deal with second order ODEs in the derivation, you don't have to deal with this added complexity of taking the derivative of something which is already complicated. The price you pay is that you have a larger dimensional system, because this is an n-dimensional system of second order ODEs, And now you have a 2n dimensional system of first order ODEs, right? I'm not saying that that's always optimal, but what I'm saying is that with this formulation, you will get a lot of things for free that you don't have in the original equations of motion, all the properties of the Hamiltonian system, okay, which we'll get to shortly. One thing before I get there is that also the Lagrangian, to us, at least to me, doesn't really, even after all these years, it doesn't, although I work with it, it doesn't really ring a bell in terms of physics. Now let's see if the Hamiltonian does that. If I'm better off, because it's always good to have intuitions for the quantities that you work with, because then you say, okay, that just can't be right what I'm getting from this. Or based on my intuition, I expect this quantity to have that property, right? So let's just see what the Hamiltonian comes out in this case, to be in this case. Remember what the Hamiltonian was. Let's scroll back. The Hamiltonian was, I'm trying to find the very first expression so that we still have a firm ground in the more physical quantities. Look at this expression here. It was basically the derivative of q dot. This was the Legendre transform, the derivative of L with respect to q dot, and then multiplied by q dot, and we subtracted the Lagrangian, right? So that was then the derivative in black, derivative of q dot with respect to q dot minus L, okay? But if you look at the structure of the Lagrangian, the dependence on the Lagrangian, on q dot only comes in from the kinetic energy. So when you take that derivative is unaffected by the potential completely. So when in effect you evaluate this derivative, you get the derivative of the kinetic energy with respect to q dot, and you also multiply by q dot minus L. Now, T is a general function of q and q dot. I haven't assumed too much other than the fact that the Lagrangian is convex in q dot, and therefore, since the potential energy doesn't depend on q dot, that actually implies the convexity of the kinetic energy. And I said that was making sense. I need to assume a little bit more about T, which is still the physical. And I need to that is just, to that I just, for that, I need to make just one definition here and then recall a result, which I'm giving you because I think this is an important general piece of information. So a scalar function doesn't need to be a scalar function, just generally speaking f, all right, of some variable x, which I assume that it's once continuously differentiable and x is taken from Rn, okay? So a scalar function like that is called positively homogeneous of order, let's say d, and d is a natural number if, so here's the definition here, positively homogeneous of order d if the if for all constants, which will be scaling factors that are positive, I find that if I scale the argument of the function by that lambda, then it's just the same. I can pull out lambda with the dth power on it and multiply by f of x, okay? So this looks like an esoteric definition, but it turns out to be incredibly useful in mechanics, or in fact in variational calculus in general. I mean, I used that in different contexts that had nothing to do with classical mechanics, okay? So for instance, if you have a function like this, say the square root of the inner product of x by itself, okay? Then so this would be your f of x. If you then evaluate f times lambda x for any such lambda, and imagine putting lambda in here. So lambda is here, lambda is there. So you can pull out lambda squared, and you can take the square root of lambda squared, which is lambda. So this is equal to lambda times what you had originally. So this function is positively homogeneous of order d equals 1. And you perhaps now see the reason for the positive homogeneous. And you could say, well, why do I insist on some positivity for lambda? Because the types of functions that you deal with very often when you calculate distances and you would try to minimize distances and energies and whatnot, they involve these types of terms. And this is not generally homogeneous with respect to lambda. If you feed in a lambda which is negative, all right, then when the dust settles, lambda squared will rise under the square root. But when you take it out, you will have the modulus of lambda, not lambda. So that would swap the sign, the square root. So this is a better, more general condition because it doesn't require this relation to hold for all lambdas, only for positive lambdas. So it's more forgiving than requiring it for all lambda, because for all lambda, this homogeneity would not work. It would flip the sign of lambda, right? So I'm not testing the function for all lambdas, only for positive ones. And this is one of the reasons, right? So this is just a remark in parentheses, just to give you an example of that. Now, why did I introduce this? There's a great theorem, which is, again, for all I know, I think it's Swiss made by Euler. Euler was an incredibly productive mathematician, although one has to add that most of what he produced was not in Switzerland, but he was a distinguished guest, as I understand, of the Tsar in Russia. So his greatest results were, so he was getting, a nice salary and working there. But nevertheless, this is again Swiss made. So Euler's theorem is the following, incredibly useful, that F is positively homogeneous for order D. It's actually equivalent to the following, that if you take the gradient of F with respect to its argument, right, and you take the inner product of that with respect to X, then that's the same as D times F of X. And let me actually write out the arguments. And I just write the inner product like that, okay, equals D times F of X. So this is both, this is unfortunate, right? Because it seems like I'm taking the derivative of D. Well, that's why I use the gradient here. This is really the derivative. Okay, in this case, this is just a constant. Now, why did I pick that constant? I could have picked something better. Well, just for this discussion, so we don't get confused. My apologies. So of order D, like we could D tilde. I just want to point out that this has nothing to do with the differential, all right? That's a constant. So that tells you that either when you do this to a function, so you would have to differentiate the function and then multiply by its argument. Normally, you would have to know what the function is, right, to do this. But for positively homogeneous functions, you don't have to. You just take that homogeneity parameter and you multiply the function by that, okay? And this is an equivalence relationship, so you can also use this as a test for positive homogeneity. If this is true, then you don't have to verify this, for all these, but this is the case, right? So that was an aside, and the reason why I did that aside, but because you might see that despite the typo that I made here, because that should be a Q dot right there, that's actually what I'm doing to this kinetic energy. I'm differentiating it with respect to its argument, and I multiply it by Q dot. So if I assume something very reasonable about the kinetic energy, just based on the physics of the kinetic energy, that is basically a quadratic function of Q dot, right? It's basic. I don't want the details, but it's basically some sort of quadratic function of Q dot, but its coefficients may have a general dependence on Q and T, okay? And mind you, the kinetic energy, then it could be something like the square root of something even. So this points beyond mechanics. So I could have, the square root of this further squared. And then I would need the notion of, and maybe that could be part of the kinetic energy, right? So it doesn't have to be just a boring second order polynomial if it falls in this general class. So if T x dot is a positively homogeneous function of x dot with of order 2, so it's then when I do this operation, I differentiate with respect to q dot and multiply by q dot, I'm doing exactly what Euler's theorem is all about. And you know, he came up with this theorem for a reason, precisely because these types of things arise a lot in calculus of variation problems. So I can just go ahead immediately write that this is 2 times t, which is a function of q dot, right? So based on that, if I then, this was the assumption, which is very physical assumption, because all the kinetic energy expressions, no matter how complicated they are, they fall in this general order or general framework. H, look at this formula here. This is just 2t minus L. So 2t minus L, but let's not forget what the Lagrangian was. That was t minus v by itself, kinetic minus potential. So that's just t plus v. So in the very general conditions, I don't even have to have, you know, strictly speaking, I don't have to know anything about the kinetic energy. This is always the case. So what's this, the total mechanical energy? And all of a sudden, therefore, I work with a function, the Hamiltonian, which has a meaning. So for mechanical systems that have geometric constraints, so I need to be in this framework, and also the potential forces, all the forces were potential, and they could have been time dependent, but potential. H has the meaning of the total mechanical energy. So for any mechanical system. Which, you know, it has to be holonomic, and it has to have potential forces. So that's a big plus, because all of a sudden then you have a system of equations which should please physicists. And, you know, that's why in the physics literature, this is really a whole lot more prominently featured than in the engineering literature, is that you can actually have an expression for your total mechanical energy and derive an equation of motion for any system of any dimension directly from the energy. And that's a big plus. Because again, immediately that comes with a lot of intuition. So if we do an example in the example, I think this is example 1.1, I labeled it. Any questions on this, by the way? So our standard example has been for nonlinear systems, the pendulum equation, right? Because it's not trivial, but it's also not too complicated either. But I don't want the curved pendulum, I want the straight pendulum. Okay, good. So you have gravity here down there, moving down there. And I struggled with that expression because I didn't want to go into it, but now I see I should have, that all the external forces are potential. But it's not true that all the forces are potential. I have no idea what the constraint force here is. And if I did Newtonian mechanics, which all of us have done in high school, we spent a lot of time figuring out this force here, right? Because we had to write down the equation of motion. Now I know nothing about this force a priori. It may depend on, you know, position, velocity, and whatnot. I don't know if it's potential. Generally, it's not. But it turns out not to matter because that's an internal force, internal to the system, which is a constraint force. All the external forces have to be potential. And here, the only external force is just G, which is coming from a potential. So it looks like it's unavoidable. Let's see. So all external or active forces, I should say, not constrained forces, active, because that's what I was struggling with that expression here. So it just means that it's not arising from constraints, okay? But it's really, It can be coming from interactions between two of these bodies that form the mechanical system. It can be an external force, but it's not coming from an interaction between the mechanical system, the original mass, and some constraint. Okay, so this is the pendulum. And the only external force, again, active force, which is not constrained force, which is the gravity, force of gravity, it's the potential. Okay. Now, my objective would be to skip the Newtonian equations of motion, skip the Lagrangian equations of motion, just derive the Hamiltonian equation of motion. But to get to the Hamiltonian equation of motion, you generally need the Lagrangian, because that's part of the definition of the Hamiltonian. So let's start with the Lagrangian. So the Lagrangian is the difference of the kinetic energy and the potential energy, right? I will need a generalized coordinate. This will be phi. It's already an example. If you did Newtonian mechanics, right? It's strictly speaking, then you would introduce x and y here, and you would have two equations of motion, but and then you would include the constraint force, and that's quite a procedure. This is a simplified procedure in Lagrangian mechanics, but you already have to have a generalized coordinate which is consistent with the constraint. The constraint here is that your mass lives at the end point of this bar, and that bar is then all it can do is it can just rotate, right, on this point. That's quite some constraint, and because of that constraint, that's enough to know the position of the bar. Once you know the position of the bar, then you know the position of the mass. So it's enough to have this one generalized coordinate, even though this is a planar motion, which normally would require two coordinates in Newtonian mechanics, right? So I then express the kinetic energy, which is a function of phi and phi dot. In general, this is a function of phi dot, but it's simple here. It's mass times velocity. So I write 1/2 times mass. And what's the velocity? The velocity here is an only tangential velocity. That's going to be L times phi dot. Positive in this direction, positive in that direction. Sign doesn't matter because I have to square it anyway. So this is L times phi dot squared. That's the kinetic energy minus the potential energy. That's something we already, I think, looked at in the first semester. Just need to see what this increment in height is once you displace the pendulum from its position at rest, which I will take to be the zero position of the potential energy. So that's just mgl times 1 minus cosine phi. Okay, when you work that out. We did that for the pendulum before. Okay. It's some geometry. So this is t minus v. That's what I have. So in order for me to move forward in the Hamiltonian direction, I need to have a generalized momentum. So the definition of P, I can do that. Before I go there, is this leading anywhere? Am I going to be able to do the inversion between P and Q dot? Remember, that was an important point here. That I can formally, I'm on my way to calculate the Hamiltonian, and I can always define P to be the derivative of the Lagrangian with respect to Q dot, but this step was absolutely crucial. I had to have a convex L for this to work. Convexity of L, I didn't finish that sentence, right? So before I check, and I told you that's usually the case, but let's just make sure that that's indeed the case here. This is L, the convexity of L in Q dot translates to the convexity of the kinetic energy in phi dot, because this, from that point of view, this is just a constant. It doesn't depend on phi dot, right? And sure enough, this is a quadratic function, a parabola in phi dot, so this is convex in phi dot. So let's just check. Let's just point it out. This is convex in phi dot, so that's okay. So I can go ahead with my construct and define P to be the partial derivative of L with respect to phi dot. Phi is not my Q, which is the single generalized coordinate. I can proceed with that. That's just m times L squared phi dot. And there you go. This is the relationship that we have guaranteed, that I can now express that Q dot uniquely as a function of P. So phi dot from here is just, this is that F relationship, which was so mysterious. except for the current case, it's just a very simple relationship. So this was our f, which told us that we have a function that should be a position function plus phi dot plus t. But in the current case, because it's so simple, there's no explicit dependence on phi and there's no dependence on t. Okay, so this was that inverted relationship. Where this is the point where I'm passing to a new set of coordinates. I will keep phi as one of the coordinates, but I'm exchanging the velocity coordinate into a momentum coordinate. Okay, so then the Hamiltonian, which remember is the Legendre transform, is p times, so this is a fresh expression, so we'll probably have to go back still and just remind you if you haven't seen this before. This is how you proceed. This is the Legendre transform. This is how you get the Hamiltonian from the Lagrangian. Okay, so I need to do the dl d phi dot and multiply by phi dot and subtract L. Now I remind you that this was just P. Okay, so phi dot I already have. So the first term here is P times phi dot, but phi dot is there. So that's going to be P squared ml squared. Now I still have to subtract the Lagrangian. Now the Lagrangian is kinetic plus potential. I know what the kinetic energy is. It's right here. But now for this to work, I have to use this relationship for phi dot and plug in. I have to express phi dot. Whenever I see phi dot, I need to use the expression for P. When you plug that in, it actually just comes out to be 1/2 P squared ml squared, okay? Minus the potential. The potential is unaffected by this change of coordinates. It only depends on phi, okay? So ultimately, what this comes out to be is 1/2 times P squared ml squared. That's the new kinetic energy term that replaces the original one after this manipulation, plus mgl times 1 minus cosine phi, okay? And you can verify, as it should be, that this is just the total energy of the system expressed in terms of the new coordinates, the generalized position and the generalized momentum. So this is the total mechanical energy. All right, so in particular, this is now T, and this always has been V. But the sign of V in the whole discussion has flipped to something for which we have intuition, right? T plus V, okay? So then essentially I'm done, because the advantage of Hamilton mechanics is just enough to have this function, right? I mean, I can write out the equations of motion for myself to remember, but a lot of the things I can now do, all of the analysis, without ever writing out the equations of motion, if I then utilize the general properties of Hamiltonian systems that we will shortly cover. However, just for completeness, the Hamiltonian equations of motion is just so that the first component was Q dot, right? Again, just scroll back here just to remind ourselves. For any mechanical system, this will be the equation of motion. So Q dot is just phi dot. And what I need to do, I need to take the P derivative of H, so the partial. That's going to be P over ml squared. And then P dot minus will be the minus the negative derivative of H with respect to phi. So that's going to be minus mgl times sine phi, because I have a minus there to begin with. But when I differentiate this part of the Hamiltonian, I will get a minus sine phi, which cancels out this minus. So minus minus is plus, plus I have the minus there because of the skew symmetry of the Hamiltonian construct. And that's why I get that equation, right? So this is then the equation of motion in this case. Hamiltonian equation of motion. Okay. So any question of that? And just the terminology, this is a 1 degree of freedom Hamiltonian system. Okay, mechanics. The term degree of freedom works or is used also when the system in Hamiltonian mechanics, if the Hamiltonian dynamical systems, even if it doesn't come from mechanics, although the original motivation is mechanics. If there's no questions on this, let me do another example. So this will be example 2 from a different area, not classical mechanics. This will be fluid mechanics, and let's look at 2D incompressible fluids. And again, certainly if you're a mechanical engineer with a master's degree, you cannot escape having seen 2D incompressible fluids, but perhaps from a different perspective. I can describe the motion of a 2D incompressible fluid by these 2 variables, x, y. They're taken from R2, right? And incompressible, that there will be a velocity field governing the motion, time dependent in general, and v as a vector will have 2 components, u and v. Okay, and the incompressibility condition just means that the divergence of the velocity vanishes. So the ux plus vy equals 0 identically. That's incompressibility. Divergence free vector field governs the motion of fluid particles. Very often in fluid mechanics, it's the Eulerian view that prevails, and people almost exclusively talk about the velocity field and properties of the velocity field. But that's not what the fluid does. Very important to remember that. What the fluid does, actually, the fluid particles, is what the solutions of this ODE do. And if your true interest is the solutions of this ODE and not the velocity field by itself, then whatever you do on the velocity field by itself will not tell you what the fluid does unless you have a steady velocity field of this dynamical system. Then say what we'll get to say streamlines of the velocity field directly tell you they are trajectories of this ODE. But if you have time dependence here, that's no longer the case. Right? I can't understand a non-autonomous dynamical system just by taking a look at its right-hand side at various times. That can be very misleading. Think about if that was the case, the whole idea of chaos that we have described would be out of the window, because I would just look at the time-dependent equation of motion, the forced Duffing oscillator. I would freeze time on the right-hand side, and I would plot always nice regular trajectories with a frozen time system. I would never see any chaos, right? Likewise, in fluid mechanics, there's a big realization that even two-dimensional incompressible flows like this, they can show chaotic particle motion, even though the velocity field, which is the field on the right-hand side, when you freeze time, it will have completely regular streamlines, right? There's no indication of chaotic behavior. So this is a big message to the fluids community. 70s, 1980s, I think, where Hassan Aref had a number of papers pointing this out. It was known in the math community, but somehow the two communities, the more engineering, physics type fluids community and math community were not talking so much to each other at the time as they do now. So the physics is that you have some, spatial domain in which, just for simplicity, for the picture, things are bounded. So this is in R2, and it's fluid, so the trajectory has to be blue, obviously. And this is what a fluid particle does. I mean, that's an abstraction, right? I mean, the fluid is a continuum, but in continuum mechanics, when you view things through the eyes of continuum mechanics, there's the assumption that you can take a small enough volume so that that volume is essentially shrinking down to a point, and by itself, that's a good representation locally of all the quantities that you can measure in the fluid. So it makes, in reality, that's always a little cube, right? So anything you measure has a distribution, but below a certain scale, you say, I can't really resolve that anyway. So the continuum hypothesis is that all these have a pointwise limit, and it makes sense for me to talk about that material point, although that's really an abstraction, right? You could not follow really a point. It has to have a finite extent. But that's sort of just sort of rambling about continuum mechanics to say that to some in fluids, they say, what do you mean a fluid particle? What is that? You mean something I put in the fluid, right? Say a little ball, right? No, it's the limit of fluid motion well-defined continuum limit associated with in principle, with the motion of a point of a fluid, even though that doesn't exist, right? So tangent to that, you would have the velocity at xtt, and then the motion of the fluid is particles. This is the equation of motion of the fluid. Okay, so incompressibility in this case can be rewritten in a whole lot more complicated way, which first doesn't show its advantages. I can take and extend this velocity field into a three-dimensional velocity field and also swap some of the entries. So I consider this velocity field instead. It's a fictitious 3D velocity field associated with the original 2D velocity field. The reason I'm doing this, that I can rewrite the incompressibility condition, as you can check in a second, as a curl-free condition for this extended velocity field. So if I now, so this is basically this is not simply the velocity field extended to 3D, because that would be just uv0, right? I can view this in 3D if I want, if I had 0, but this is other than that. This is a fictitious velocity field. However, it will serve my purposes as well, and the main reason is that I can now say that this fictitious velocity field is curl-free precisely when the original velocity field is incompressible. Okay, now the nature of the curl is such that you will have to evaluate the curl. So the third component of the curl. So how do I do that? I, j, k, then I need to take dx, dy, dz, and minus v, u, 0. Okay. Now, why is this 0? The I components is the only way I know how to say it. Still, after all these years, I always forget the components. So the I component of the curve will be that I need to take this determinant, right, formally. So when I take that determinant formally, then I will have to take the y derivative of 0, which is 0. And then I have to subtract the z derivative of u. But u is a two-dimensional velocity field. It only depends on x and y. So that z derivative of u, which I would get formally as a product of these two terms, is also 0. Okay. Now I go for the j component, right, which would be this determinant minus j times this determinant. But again, I'm taking the x derivative of 0, and I'm taking the z derivative of v, but v doesn't depend on z. The original velocity field that I'm working with here only depends on x and y, so that's also 0. Okay. Now what about the third component? Third component the k component would be this determinant, right? So I have to take the x derivative of u, which I can luckily take, and then I have to subtract this formal product, okay, which is but I have a negative there, so that's just the y derivative of v, right? But that is 0 precisely when I have an incompressible flow, because that was my condition here, right? This is true by incompressibility. So this is just a complicated way of rewriting incompressibility, but also turns out to be incredibly useful for the following reason. One advantage of working in 3D is that I have a potential theory in 3D, which we learned in vector calculus. At least that's where I learned it back then. And again, this is an incredibly useful tool, very powerful tool. Basically says that on a simply connected domain, in 3D, if I have a curl-free is equivalent to potential. So any vector field that has vanishing curl on a simply connected domain has a potential function. Okay, so one can write that velocity field as the gradient of something, right? So if my original field domain D was simply connected in 2D, all right, then when I erect what's simply connected, it means that if you take any 2 points, no, sorry, that's path connected. Simply connected means that if you take a closed curve within the domain, then any closed curve, then the interior of that closed curve is also in the domain, right? So you cannot have holes in the domain. So if I work with such a domain and I simply add the Z component, then that will be a simply connected domain in 3D as well. So if I make that assumption here, which I have just added now, all right, then I'm in this setting. So that means that since I have curl free for this extended velocity field, I can conclude that there exists, all right, a potential, which is usually called the velocity potential in this case. Psi, let's call it psi, right? It's a function of x, y, z, and t, because I'm working in a time-dependent setting. All these velocity fields carry time as a parameter. Even though this argument is taking place in space, I'm carrying t as a parameter. And now I'm working in 3 dimensions, so I have to have z as well. And I should be able to write minus v u 0, this extended curve-free velocity field, as the gradient of psi. That's what it means to be a potential velocity field. I have a potential function associated with that, all right? Now let's just read off the implications of this. Let's start with the last one. Remember what this is. This is the x derivative of psi, the y derivative of psi, and this is the z derivative of psi, all right? So if I look at the last row, it tells me that in fact, for this velocity field, I look at the last one here, it doesn't depend on z. So psi, although mathematicians don't like this, but they say the symbol psi, you either refer to it as a function or you refer to it as the evaluation of a function, right? And these are therefore incongruent with each other. This is a function and this is a value. So the two are cannot be equal. Nevertheless, this is what's used a lot in practical courses to point out that the dependence of a function on arguments. So there's no z dependence, right? There is, however, I made a mistake here, dependence on t. All right. So once I have that, then okay, the last bit did serve its purpose. The last row was telling me that this psi actually only depends explicitly on x and y. And then I look at the first 2 rows, and then when I compare this here, then I get that minus v is the x derivative of psi, right? And I get that u, which arises here, is the y derivative of psi. So if I go back to my original ODE, which was here, and whose right-hand side was simply the velocity field, which was u and v, okay? Then I can rewrite that ODE now as x dot equals u, right, in the first component. Why don't I write out both components so that I don't have to carry the underscore. X dot equals u from the u velocity, but I have just learned that that's the partial of psi with respect to y. And y dot is equal to v by definition, but I have just learned that v is just a negative partial of psi with respect to x. So that's this negative partial. So there you go, another Hamiltonian system. And what is the meaning of this Hamiltonian again? So this is a 1 degree of freedom Hamiltonian for the fluid motion. And as promised, this has always, well, most of the time, physical meaning. What's the physical meaning? Well, this is called psi is called the stream function in fluid mechanics. is the Hamiltonian. Okay, so completely different area. The key here was conservation of volume or area by the flow, and on a simply connected domain that leads to a Hamiltonian formulation. Okay. Any questions on this? Very quickly, example 3, because I've talked a lot. Take a planar, autonomous, any kind of system, biology, chemistry. But assume it has a conserved quantity. Clearly, that has nothing to do with mechanics or even fluid mechanics. It's just that a general OD at x dot equals fx because it's autonomous, and there exists a function u. Yeah, I'm just sloppily say that u is defined on R2 and it maps to R, so it's a function such that when I evaluate u along trajectories, along any trajectory, then I find that it turns into a conservation law. Along the trajectories, u is constant. Let's just assume that. And again, this can really come from any area. This can be the result of some mechanical, physical property, some conservation law, but it can be the result of some symmetry or anything, just happenstance. Maybe for some parameter choice, this is the case. This is in this case, this is called u is called the first integral traditionally. What is a conserved quantity? In that case, what I know is that if I take this the derivative of u along trajectories, right, then that derivative should be 0. Now, what's that derivative? By the chain rule, I first have to differentiate u, so I get grad u, and then I have to dot it with x dot, and that's identically 0. So what does that tell me physically? It tells me that if I look at the gradient of u, and then at any point, that gradient of u must be orthogonal to x dot. I don't exactly know. I had to take the orientation of x dot for the purposes of this picture. I don't know what the magnitude of delta grad u is. I don't know if it was actually really pointing upwards in this case or downwards. So this is just one possible case, but the emphasis is more on this right angle. Because of that right angle, I'm sure then that at any point I can write x dot as the rotated image of grad u plus some scaling, or in addition to some scaling, because I can't simply rotate x dot into grad u. Nobody said that a rotation would give me grad u. I will also do then the right scaling to the right length. But I can then certainly do this. I can take grad u, I rotate it by 90 degrees, and it doesn't matter which way because the scaling can be negative if I rotate it the wrong way. So I pick one particular rotation j, which I prescribe to be 1z minus that. That's a 90-degree rotation. And then I will include a scaling here, a position-dependent scaling. I have to, then scale that rotated image to exactly hit the value of grad u, and that can potentially be negative because this rotation, for all I know, may have rotated me in this direction. Okay, and the px is just then is a location-dependent scaling. So what this gives me, just rewrite it now with more space, x dot equals some function p of x times this J matrix, which mind you is the 2D canonical symplectic matrix. And then I had in my previous notation, I would have written just d of ux. And this is actually, so far, what I've got is not quite yet the canonical Hamiltonian system, but it's called the generalized Hamiltonian system because it's almost like a Hamiltonian system, The only difference is this scaling factor here. But that's a scalar. We will be able to scale that out next time. Generalized Hamiltonian system. Okay, I'll stop here. Maybe I just add, because it's, then I have to recall the, if you forgive me, just rescale time by introducing in each trajectory a new time, tau, which will be integral from 0 to t. You take the scaling factor, whatever it came out to be, you evaluate it along the trajectory and integrate it. Okay, and this integral will give you a new time. I assume that p doesn't vanish. So in the new time, by the chain rule, the dx dt, which is the left-hand side of this equation, but the chain rule, that's just dx d tau with respect to the new time times d tau dt. But if you look at d tau dt from this here, that's just p of x. Okay, just a note. Now, on the one hand. On the other hand, I have the right-hand side of the ODE, of this ODE, which is j dux. So here comes the usual dirty trick that we, on both sides, I have this factor px, I cross it out. So therefore, I get that in the rescale time, x prime, I denote this by x prime, I simply get j dux. And there you go, that's just precisely a canonical Hamiltonian system. One degree of freedom Hamiltonian system. And the Hamiltonian, and again you say, what's the meaning of the Hamiltonian? Again, it has this meaning that you knew one thing about your system, that it conserves an important, some sort of important quantity, and that's your Hamiltonian. So already in 3 examples, you've seen that the Hamiltonian tends to have an important meaning for the system. It's always nice to work with quantities for which you have intuition. So let me stop there. Sorry, I'll give you back next time the extra time I took. If there are any questions, I'm happy to answer now.
Professor?
Yeah.
Yes, it's me. I might have a question regarding last lecture about the Newton-Raphson method.
Right.
So just like a general question, actually. We proceeded so in order to show that the method is chaotic, basically we proceeded to show that the sigma is a Cantor set.
Sigma was, yeah, the big sigma, right?
Yeah, the big sigma. Right. And then from there we inferred that the mapping on that set is chaotic. Why exactly does this follow? I mean, we had a theorem in I think when talking about the irreducibility of the matrix A. Right. But these equivalents between sigma, the big sigma is a Cantor set, and that the mapping on that set is chaotic. I mean, did we show that or?
No, we didn't. So that was part of the theorem. If you look at, I hopefully stated that way. So there were 2 statements there. Yeah. That if the transition matrix is irreducible, I don't know where we can.
Yeah.
So if the transition matrix is irreducible, then the set is a Cantor set. And the second was that this is a chaotic map.
Okay.
Which I didn't prove. That's a bigger theorem. We did prove that, and partly also with the homeworks, for the classic sigma, which is the classic Bernoulli shift map without the restrictions, right? This would require a separate argument, but as long as the full set is, you haven't killed off, all interesting behavior, the full set is still a Cantor set, then the shift on that restricted set is still chaotic. That we haven't proven. It's I just listed that as a theorem. So it would be the references that I listed I don't think that any of the first line references that I give you would have it, but you would have pointers then.
Okay.
To this proof.
And the second question is about these Cantor sets. So at the beginning, I think we had the property that these sets are, what was it, totally disconnected.
Right.
Now for the Newton-Raphson method, this was not the case, I think we said.
Why?
I mean, we didn't see anything about that. We just said, I think that the method is, that the mapping is closed and non-empty. But there was this additional
closed and not empty. But I also added, perhaps only in words, that one would need to make an additional argument. Well, where was that? To show. Sorry, I'm missing it this point. Yeah, somewhere here. Did I? Here. Yeah. See, the missing bit here normally requires work to show that these components that you get are points, so that they actually shrink down to a single point.
Okay.
And in this case, that comes out from the fact that the map has we have control over the derivatives of the map, so we can give uniform lower and upper estimates for the derivatives, and from that. I was waving my hands to show that. Remember, perhaps here, doing this, right? So that means that from this, you can conclude a uniform minimal shrinkage in each and every step. And if that uniform minimal shrinkage applies to the preimage of any step, okay, any set, sorry, any closed interval, then it has no choice but shrink to zero, because when you take infinitely many times preimages, it gets contracted by uniform factor. That it has to shrink on a point as opposed to anything else, right? So it's all a Cantor. It's a Cantor set of points, okay, within I1 and I2 and I4, right? I3, I4, right?
But I think in the notes you've written connected set in the notes. So if you scroll down just a second.
Here you mean?
Yeah.
What I meant to say that at each and every point, at each and every step, you have a connected set, right? So that means that when you're zooming in, you're taking more and more intersections, that at any finite point, the set is connected and closed. And when you're at a finite step in your construct, it will indeed be a closed interval. But when you take the limit, the closed interval will shrink down to a point. That's what I meant to say. Yeah.
When the limit basically becomes disconnected in that sense.
Well, don't forget that this set, right? This particular set corresponds to a particular symbol sequence that I'm chasing, right? It's not the entire set. I'm zooming in. I picked one symbol sequence, and I'm trying to argue that for that one symbol sequence, there is a unique point in the interval, right? So I'm not worried at this point about the whole set. I don't need to get a Cantor set from this construct because I fixed one symbol, right? And that one symbol goes to a single point. Then I turn around and say, wait a second, that symbol was an arbitrary symbol from a Cantor set, okay? Therefore, for each and every point, I will get such a point, so that the image is also a Cantor set under this homeomorphism, right? So the end of this construct is a single point, a connected single component, just one point, right? There's perhaps a confusion that I created here. There's two things. There's the Cantor set and there's Cantor's theorem. Cantor's theorem by itself doesn't guarantee, it's not talking about Cantor sets. It just says that the intersection is not empty, right? And I'm using Cantor's theorem to conclude that I get this one point for one symbol. Now I pick another symbol, I get yet another point, another symbol, yet another point. And then I say, I have a Cantor set of choices for the symbols, therefore I must be getting a Cantor set of points. Right? Okay.
Thank you.
Sure. Anything else? All right. Then I have nothing else to say. I think you guys are set with the homework. You have one that you have to turn in. I believe it's next week, right? The deadline, if I'm not mistaken. Please take advantage of the office hour if needed. And then that's it for now. Have a good weekend, which is still far away. I said have a good weekend because I already think about seeing you next week. But I mean, there's still some time between now and the weekend. But anyway, have a good weekend. Bye.